In this video, I'm going to walk you through the different subatomic particles, how to find them, and we're also going to use your periodic table here to get information about different atoms. So if you don't have your periodic table out, it would be a good idea to get your periodic table out. It's probably a good idea to have your periodic table as you do interact with these note videos kind of from here on out, because we start to really use that periodic table uh, to do the notes and the content. So, what makes atoms of different elements different from each other? So, why are these atoms different? And the key here is it's all about the number of protons. Every atom has a different number of protons for each element. All right. So, atoms of aluminum have a certain number of protons, which would be different from the number of protons for atoms of chlorine. So, it's the number of protons that tell you which element is which here. All right, so the number of protons are very important. The atomic number is the number of protons. All right, so you need to know that the atomic number means the number of protons. In order to determine the atomic number or the number of protons for any element, you use your periodic table. You do not have to memorize the atomic number for any element. You will always have your periodic table for this. You just need to find the element and be able to look up the atomic number. Okay, so for example, all hydrogen atoms have one proton, so the atomic number of hydrogen is 1. If you find your periodic table, all right, go to hydrogen, should be element number 1, all right, and confirm that you can see that hydrogen has an atomic number of 1. If you look on your periodic table, there's usually a key which tells you what each number and symbol mean in the box. So look at the key and then you'll know which number on the table is the atomic number. If you're using the periodic table I gave you, it's the number above the element symbol. So if you look at this sample periodic table over here on the right, this is pretty much how your periodic table is set up. So you have the symbol here for the element and the number on top. That's going to be the atomic number or the number of protons. So now using your table, you should be able to look up the atomic number of any element. All right, and you don't have to memorize it, you just have to use the periodic table. So right now, try these 4 examples. Look up the atomic number for each of those 4 elements. Pause the video if you need to, and then when you come back, I'll just quickly write down how many there are for each. So pause the video, look them up, write it down, and then we'll see. All right, so I'm going to just continue this and give you the atomic numbers for each of these. So when you look these up on your periodic table, lithium has an atomic number of 3, so it has 3 protons. Lead would have an atomic number of 82, so he would have 82 protons. Au is gold. Gold would have 79 protons, and bromine would have an atomic number of 35. So make sure you got those answers and make sure you can look up the atomic number, the number of protons for any element using your periodic table. Now you know how to find the number of protons for any particular element. So then let's work on the next subatomic particle, the electrons. All right. As long as your atom is electrically neutral, meaning it does not have a plus or a minus charge, that means the positives and negatives must be equal. So if you know the number of protons, which are the positive particles, then you know the number of electrons as well. They must be equal as long as the atom doesn't have a charge. Okay, so once you know the number of protons, now you know the number of electrons. All right, it's just that easy as long as there's no charge. So atoms that have different numbers of protons and electrons here, those are called ions. All right, ions are charged particles, meaning they would have a plus or a minus charge. So sometimes the protons do not equal the number of electrons, and this is going to be called an ion. All right, but only the electrons can increase or decrease here to give ions, not the protons. Why can't the protons change? Think about this. Why can't the protons change? If you change the number of protons, you would change the element. All right. Each element has a specific atomic number, a specific number of protons. You cannot change that number. So in order to have a charged particle here, the only particle that can change is the electrons. All right. So make sure you're thinking about this here. If an atom has a positive charge, it lost electrons. People always get this confused. All right, think about it. Electrons are negative. So if you lose negatives, you are now more positive. All right, and if a particular atom has a negative charge, that means that electrons must have been gained because electrons are negative. So if you gain negatives, you now have a negative charge. And how many you gain or lose here is going to determine the exact value here of the charge. So for example, okay, Mg2 plus. All right, magnesium likes to form a 2 plus charge. We don't need to worry about why or anything like that right now. But magnesium, when he forms a charge, forms a 2 plus charge. So that means the protons are not equal to the electrons for Mg2 plus. Okay, in order to be magnesium, magnesium must have 12 protons. All right, that number cannot change. I looked up magnesium on the periodic table. I found the atomic number for magnesium. It's 12. All right, but because now he's a 2 plus charge, that means, okay, he must have lost 2 electrons. So magnesium 2 plus does not have 12 electrons, it only has 10 electrons. Essentially, it has 2 more positives than it does negative particles. Okay, so when an element is positive, it lost electrons. Another example here is nitrogen. Nitrogen likes to form a 3 minus charge. All right. Again, you don't need to worry about why. That's just what he likes to do. All right. So the key here is if you look up nitrogen on the periodic table, in order to be nitrogen, nitrogen must have 7 protons or 7 positives. All right. But if he's 3 minus, all right, that means he has to have 10 electrons. Okay. He's not equal here. If the protons were equal to the electrons, it would just be normal nitrogen with no charge. Because it's N3 minus, you have to have 3 more negatives than you do positives. All right. So if you have a negative charge, if you're an ion with a negative charge, you have to gain electrons. So just be careful with that. If a particular atom has no charge with it, the protons must equal the electrons. And if there's a charge with it, you got to think about what happened here in terms of losing or gaining electrons. We now know how to find the protons and the electrons for any particular element. So what about the neutrons here? All right, in order to figure out the neutrons, you need to know something here about mass number. Mass number is the total number of protons and neutrons in an atom. All right, so mass number means protons plus neutrons. Very important to remember here. Mass number is protons plus neutrons. Um, Technically, this number is not on the periodic table. You can round a number on the periodic table to get the most common mass number for a particular element. It's the most common isotope mass number for a particular element. We'll talk about isotopes in a little bit. But the key is this number is technically not on the periodic table. You can round a number on the periodic table to get the most common mass number here, though, for any element. All right, so we have to use mass number to figure out neutrons. That's the last subatomic particle we're still trying to figure out here for every element. We know how to do protons, we know how to do electrons, so it's just neutrons. So think about this. If mass number is protons plus neutrons, if you want to find the number of neutrons here, just take the mass number and subtract away the protons, and you'd be left with the neutrons. So if you're ever trying to figure out the number of neutrons and you are not subtracting, you did not do it right. All right, you must subtract to get the number of neutrons. So let's try this example here. This example says an element has an atomic number of 34 and a mass number of 78. And then you want to be able to do these 4 things. So I would say right now with your periodic table, pause the video, try it, and when you rejoin, we'll make sure you get the right answers. So pause the video and try it. Okay, so if you were doing this here now, the first question here says, what is the number of protons? All right, so they told you the atomic number. The atomic number is the same thing as the number of protons, so it's got to be 34. All right, neutrons. Now, they want to know the number of neutrons. They gave you the mass number. Remember, mass number is protons plus neutrons. So if you just subtract away the protons from the mass number, you'd be left with the neutrons. All right, so you take 78 minus 34, and you should get 44 neutrons. Remember, you must subtract to get the number of neutrons. And then they wants to know the number of electrons. So it doesn't say anything here about this element having a charge. So we have to assume that it's neutral. So therefore, protons must equal the electrons. So it's 34 as well. All right, so you just figured out the protons, neutrons, and electrons, the number of subatomic particles for this element. And then the last thing here says, what is the symbol for this element? All right, so the key is the protons tell you which element it is. So if you have 34 protons, an atomic number of 34, go to the periodic table, find element number 34, and you should see that it should be Se, selenium here. All right, I just want you to realize that you could write this a little bit differently. You could write this as selenium dash 78. Essentially, you're saying this is selenium with a mass number of 78. That number after the dash is the mass number. Or you could even write it as Se-78. That's very important to understand. There's a lot of ways you can write these things. Anytime you see an element name or the element symbol followed by a dash with a number, that number after it is going to be the mass number. All right, so that's very important to remember. So you definitely need to be able to calculate the number of protons, neutrons, and electrons for any element here. As I said, there's a number of different ways you can write these things. So another way you might see this is it could be written in atomic symbol form, which would basically be where you have the element symbol, and then the number on top in front would be the mass number, and the number on bottom in the front would be the atomic number, or the number of protons. All right, so it would look like something like this. Maybe if you're looking at this for helium, you have He as the symbol, and you have 4/2 in front of it. 4 is the mass number. That's the protons plus neutrons. Remember, you need to know this vocab here. Mass number is protons plus neutrons. And then the atomic number, the number of protons, is on the bottom. The reason why I like this notation so much is because the way it's set up, all you have to do is subtract these numbers and you have the number of neutrons. All right, it's perfectly set up so that your mass number is on top, which is protons plus neutrons. Your protons are on the bottom, so if you just subtract, you have the number of neutrons right away. So right now, I want you to try this example, pause the video, try it, and when you rejoin, we'll see how you did. So if we look at this example, it says an element has 91 protons here and 140 neutrons, and you got to answer these questions. So the atomic number of protons is the atomic number, so it's going to have 91. And then it says mass number. Remember, mass number is protons plus neutrons. So they gave you protons, they gave you neutrons, just add them up. This should be 231. And then it wants to know the number of electrons. Again, this doesn't say anything about this having a charge, so protons must equal the number of electrons, so 91. And the last thing it wants you to do is do the atomic symbol here for this element. So that means you want to do it in this notation with the mass number and the atomic number in front. So it should be 231, the mass number on top, 91, the number of protons or the atomic number on the bottom. And then when you actually look up the element symbol, you're doing this for element number 91 here. All right, so you have to find the element that has an atomic number. Remember, the atomic number, the number of protons tell you which element is which, and it should be Pa. So that's how you would do this, answering this, and hopefully that's what you got for all of these. Make sure you know the notation here for this particular atomic symbol format and know what the numbers in front mean and be able to use it to find information about any element. Some more information here about reading the periodic table. We already said that the mass number is technically not on the periodic table, but you can round a number on the periodic table to get the most common mass number. So if you look at your periodic table, the number on the bottom, all right, with the decimal typically it's the number with the decimal, is the average atomic mass. So that's not the mass number. But if you round this number to the nearest whole number, you can get the most common mass number for a particular element. Okay, it's the most common isotope mass number for that element. So for example, if you were doing this for helium, if you look up helium on the table and I said, what's the most common mass number for helium? 4.003 rounds to 4. So that means the most common mass number for helium is 4. It has a number of protons plus neutrons equal to 4. All right, so you could do that for any element here. Let's do this for boron. If you look at boron here, and I said, what's the mass number? What's the most common mass number for boron? If you don't have any other information, you go to your table, and you can see here it's 10.81. So when you round that to the nearest whole number, it's 11. So the most common mass number here for boron is 11. It has 11 protons plus neutrons. So if I said, how many neutrons then does boron have? You round this number to the nearest whole number, which is 11, subtract the number of protons, which is 5, so boron would have 6 neutrons. All right, so you need to be able to use your periodic table to do this. If they don't give you any information about mass number, you go to the periodic table, round the atomic mass to get the most common mass number that you can use then to figure out the number of neutrons. Now I want you to try a few of these. Try to determine the number of protons, neutrons, and electrons for a few elements here. So again, what I am going to stress is that you pause the video and try this. So the first one you're going to do is fluorine. Pause the video, make sure you're able to determine the number of protons, neutrons, and electrons for this, and then rejoin. All right, so when you do this here, all right, we're trying to determine the protons, neutrons, and electrons for fluorine. So when you look up fluorine on the periodic table, all right, he's got an atomic number of 9, therefore 9 protons. Doesn't say anything about fluorine having a charge, so if you know the number of protons, you now know the number of electrons. It's exactly the same. All right, so in order to do neutrons, you go to the periodic table, you find fluorine. It has an average atomic mass of 19.00, so you round that to the nearest whole number. That's 19. So remember, that's the number of protons plus neutrons, the most common mass number for fluorine. So if you want to find out the number of neutrons, just subtract the number of protons, and you're left with 10. All right, so fluorine would have 10 neutrons. Try another example here. Again, we'll do this for uranium. Pause the video, determine the number of protons, neutrons, and electrons, and when you rejoin, I'll have the answer there for you. So hopefully these are the numbers you got for the number of protons, neutrons, and electrons for uranium. Remember, you must subtract to get the number of neutrons, always. This example is a little bit more fun. I want you to try this now for Ba2+. Determine the number of protons, neutrons, and electrons. Pause the video, try it, and when you rejoin, I'll have the answer for you. So hopefully these are the numbers you got here. So if you notice on this one, barium had a 2+ charge. So when you look up barium on the periodic table, he's got 56 protons, but the electrons are not going to be equal to that. Because of the 2+ charge, remember, that means that he had to lose 2 electrons. So he only has 54 electrons. Remember, you can't change the number of protons. If you ever see a charge, you can only change the number of electrons. So the only thing that 2+ changes is the number of electrons. It just has 2 less than what you would expect if it was neutral. All right. So if it didn't have a charge, it would have 56 electrons. Because it has a 2+ charge, he lost 2 electrons, so he only has 54. And then you determine the number of neutrons the exact same way as you would. Go to the periodic table, find barium. All right. Round the atomic mass, so 137 rounds. That's the most common mass number here for barium. So when you do 137 minus the number of protons, 56, you get 81 neutrons. One more to try here. Determine the number of protons, neutrons, and electrons for P3-. Pause the video and try it. Hopefully these are the numbers you got for P3-. Again, when you look up phosphorus on the periodic table, he has an atomic number of 15, so that's the number of protons. But the 3- means he gained 3 electrons. So he has to have 3 more negatives than he does positive. The electrons have the negative charge. So he has to have 18 electrons. And you determine the neutrons the exact same way by subtracting. All right, so you should be able to determine the number of protons, neutrons, and electrons for any element, whether they have a charge or not. The next topic I'm going to talk about are isotopes. I already mentioned them earlier in the video, but isotopes are when you have atoms of the same element that have a different number of neutrons. All right, so we already know you cannot change the number of protons. Okay, you cannot touch the number of protons. If you change the number of electrons, that creates an ion. And if you change the number of neutrons, that creates what we call isotopes. All right, because neutrons participate in the overall mass of an atom, the mass number is going to be different when you change the number of neutrons. All right, so that's key to remember here. Protons plus neutrons give you the mass number, which is the mass of the element. So if you change the number of neutrons, you change the mass number. The atomic number is always still going to be the same because otherwise the element would change. You can never change the number of protons. How do you name an isotope? You just put the mass number after the element name. We kind of already saw this earlier in the video as well. So if you saw something written as carbon-12, that would be carbon with a mass number of 12. That means it has 12 protons plus neutrons. But carbon-14 also exists. That's carbon with a mass number of 14. All right, still would have, 6 protons because that's what carbon has, but now the number of neutrons has changed. Uranium-235. So whenever you see an element name or a symbol followed by a dash and then the number, that number is the mass number. So if you look over here at this example, these are the 3 different forms here, the 3 different isotopes of hydrogen. Normal hydrogen, or the most common form of hydrogen, is hydrogen 1. So it has obviously 1 proton. In order to be hydrogen, it must have 1 proton, but it does not have any neutrons. All right, if you go to the periodic table and look up hydrogen, it has a mass number, when you round the atomic mass, of 1. So it has just 1 proton and no neutrons. But another form of hydrogen exists, an isotope here called deuterium. That has 1 proton. It has to have 1 proton to be hydrogen, but then it has 1 neutron. So it becomes hydrogen 2. All right, its mass number went up essentially. All right, tritium also exists. Tritium has 1 proton, has to have 1 proton to be hydrogen, but it has 2 neutrons. So it has a mass number of 3. All right, so all that changes here when you change the number of neutrons is the mass number, not the number of protons, not the electrons. Anytime you change the number of neutrons, that's called an isotope. So let's look at this picture here for the isotopes of carbon. All right, carbon-12 is the most common form of carbon here on Earth. All right, it makes up almost 99% of all the carbon. Obviously, because it's carbon, it has to have 6 protons. If you look up carbon on the periodic table, it has to have 6 protons. All right, because it's carbon-12, this number is the protons plus the neutrons. All right, carbon-12 has 6 neutrons. 6 plus 6 is 12. Right? And if you go to the periodic table and look up carbon, the number below it, the average atomic mass, is 12.01. If you round that number to the nearest whole number, it's 12. So the most common form of carbon is carbon-12. And that makes sense because it makes up about 99% of all carbon. However, carbon-13 also exists. All right, it's only about 1% common, but it has 6 protons because in order to be carbon, it has to have 6 protons. But because it's 13, the neutrons went up. All right, 6 plus 7 gives you your 13. But carbon-14 also exists. This would be carbon with 6 protons, but it has 8 neutrons instead. So the only thing that changes when you have different isotopes here are the number of neutrons, which then changes the mass number. So when you're writing this out, okay, that number that follows the dash is the mass number. It could be different from the number on the periodic table. For example, if you look at this example below here, it says to determine the number of each subatomic particle for neon-22. All right, well, before you look up neon on the periodic table, all right, and say, well, neon on the periodic table, the most common form of neon is neon-20. All right, it has an average atomic mass of 20.18. So if you round that, the most common form of neon has a mass number of neon-20, but this is neon-22. Oh well, that's what its mass number is. So you could determine the number of protons, neutrons, and electrons for this. All right, so if you want to pause the video and try it, see what you can do, and then rejoin, and we'll see how you did. So hopefully, when you did this here, you're going to get these answers. If you look up neon on the periodic table, obviously neon has to have 10 protons. It doesn't say anything here about neon having a charge, so therefore it has 10 electrons. And when you do the number of neutrons, remember you have to subtract. This number here is the number of protons plus neutrons. It's the mass number. So 22 minus the number of protons, 10, gives you 12 neutrons. All right, so it's obviously not the most common form of neon, but it is an isotope of neon that has 12 neutrons. So protons plus neutrons gives you the mass number, and the mass number is what's going to change for these isotopes. The last major concept I want to talk about here is that atomic mass. All right, atomic mass is a weighted average of the mass of the atoms in a naturally occurring sample of the element. So it's a weighted average here. So the atomic mass is on the periodic table, all right? It's that number below the symbol with typically having the decimals with it, all right? So the atomic mass is on the periodic table. You round this number to get the most common mass number for an element on the table, all right? It does reflect the mass and abundance of these isotopes in nature. So it takes into account, what's the mass number of a particular isotope and then how common it is on Earth. And obviously it's not going to be a whole number here because it is an average. And as I said, this number is given on the periodic table. The units we use for atomic mass or average atomic mass are AMU. All right. Basically, it says here that 1 AMU is 1/12 the mass of a carbon-12 atom. So if carbon-12 has a mass of 12, 1/12 of that would be 1. So every AMU is essentially 1 here. So that you got to get used to using AMU when we're calculating atomic mass, which is what I'm going to show you on the next examples. So the key here is that this number is on the periodic table. It's not a whole number typically because it is a weighted average. Here is the equation for calculating the average atomic mass. So it looks scary. Honestly, I don't have anybody who ever memorizes this equation. You just know how to do it. It's essentially like you learn how to do the problem through the equation, but nobody ever memorizes the equation. But if you look at this, what it's showing us is you're going to take the percent abundance they give you, divide it by 100%. So essentially, you're just going to get rid of the percent. You're going to move the decimal 2 spaces to the left. All right, they're going to give you a percent. You're going to move the decimal 2 spaces to the left, and then you're going to times it by its mass. All right, so I always remember these problems as you're going to take the decimal form of the percent, times it by its mass. Decimal times mass. That's something you need to just say over and over again. I'm going to do the decimal times the mass. But the key here is this last little symbol here in the equation. That symbol means take the sum. All right. So if you were to have, say, 5 isotopes for a particular element, for every single isotope, you would take the decimal form of the percent, times it by its mass, get a number. All right. For every single one. So you'd have to do that 5 times. The last thing you would do is add up all the numbers you got. So literally, calculating average atomic mass here is that simple. You just do decimal times mass for every isotope and then add them all up at the end. All right, so we're going to go here and try an example and use this equation. Again, you're not going to, memorize this equation. Just you need to know how to use it. Just remember decimal times mass for every isotope and then add them up. So for this example, it wants us to calculate the average atomic mass of copper if copper has 2 isotopes. It says that 69.1% of all copper has a mass of 62 AMU, and 30.9% has a mass of 64 AMU. All right, so the key here is this one has 2 isotopes. So according to the equation, I need to take the decimal form of the percent and times it by its mass for every isotope. So let's look at one isotope at a time. Let's look at the first one here. It says 69.1% of all copper has a mass of 62. So first thing we need to do is get the decimal form of the percent. So 69.1% as a decimal, you're just going to move the decimal 2 spaces to the left, is going to be 0.691. I don't need to see you do that. You don't need to show your work for that. Just take the percent, move the decimal 2 spaces to the left. All right, so we need to take the decimal form of the percent, times it by its mass. So according to the problem, that isotope of copper has a mass of 62. So we did the decimal times the mass. So when you do your calculation here, it should come out to be 42.842. All right, so we did decimal times mass for that isotope. All right, and then we're going to do this now for the other isotope. All right, so the other isotope has a percent of 30.9. So you take the decimal, move it 2 spaces to the left. We need decimal times mass. So it's going to be 0.309. That would be the percent as a decimal. All you did was move the decimal 2 spaces to the left, and we're going to times it by its mass. According to the problem, it has a mass of 64. All right, so when you do the math here, it comes out to be 19.776. Okay, so all we did for each of these isotopes was we took the decimal form of the percent and we times it by its mass, right? And we had to do that 2 times because there were 2 isotopes. The last thing you do here is add them up. Don't forget to take the sum here at the end. That's it. So you just take those 2 numbers you get and you add them up. And when you do this, it comes out to be 62.618. And the units for these average atomic mass problems are AMU. You don't have to worry about sig figs here. Sometimes if these get longer, I say you can even round them to like, 2 decimal places, whatever. It's not that big of a deal. But the key is your units are AMU. So these average atomic mass problems are that simple. Just take the decimal form of the percent, times it by the mass for every isotope, and then add them up. And don't forget your AMU units. For the last example here, I want to show you a variation of these average atomic mass problems. All right, so let's look at this example. This example says the element gallium has 2 stable isotopes. Gallium-69, all right, remember, anytime you see that dash followed by a number, that's indicating the mass number, protons plus neutrons. So the other one is gallium-71. The average atomic mass of gallium is 69.7978 AMU, and we want to find the percent abundance of each isotope of the element. All right, so this is different from the previous example we did. In the previous example, they gave us the percents and they gave us the mass for each isotope, and we were finding the average. In this problem, they don't give you the percents, they only give you the masses, and then they give you the average. Okay, so if they give you the percents in the problem and the masses, you just do decimal times mass for every isotope, add them up. If you aren't given the percents, that's when you have to do this version of the problem. Okay, it's just a little bit more thinking and a little bit of math, but it's really not that bad. All right, so think about this. If we were doing a normal problem with this, we would need to do the decimal times the mass for each isotope, right? And there's 2 isotopes, so we would do decimal times mass for one, we'd do decimal times mass for the other, and we would add them up. And that would give us the average. All right, so that's essentially what we'd be doing. We would take the decimal times the mass for each of the isotopes, add them up, and that would give us the average. So let's look at this now. So if we try to do this for each of the 2 isotopes, decimal times mass of the first isotope, do we know the decimal? Well, no, because we don't have the percent. So you can't get the decimal form of the percent if you don't have the percent. All right. Do we know the mass of the first isotope? Well, yeah, it's gallium-69. So its mass is 69. But I don't know the decimal form here. So I'm just going to make that a variable, x. All right. I don't have the percent, so I can't move the decimal 2 spaces to the left. All right. Plus, well, decimal times mass for the other isotope. I don't know the decimal for the other isotope because I don't have the percent, but I know its mass is 71. So I need another variable here, but the problem is I can't use x, all right? I can't use x to represent the decimal of this one, and I can't use y because then I can't solve the problem, all right? So the key here is I need to think about how these 2% would be related. Think about this. These are the decimal forms of the percent. If they were both percent, they would add up to what? Think about it. If they were both percents, they should add up to 100% because you would have to account for 100% of the element. But this is the decimal form of the percent. So we move the decimal 2 spaces to the left. So these should add up, the decimal forms here should add up to 1. So if I take 1 minus whatever x is, that would give me the other decimal here for this isotope. All right? You really got to think about this. If this isotope here has a specific value, I know because this is the decimal form of the percent, they both add up to 1. So if I take 1 minus whatever this value is, x, I get the other decimal form of the percent here. Then what you do is you just set that equal to the average, which they told you, 69.7978 AMU. All right, so now you just need to solve this for x. So you're going to distribute through combine like terms. So we have 69x plus 71 minus 71x equals 69.7978. All right, so you want to Combine your x terms, subtract 71 from both sides here. All right, you should end up with negative 2x equals negative 1.2022. You want to solve for x, so divide both sides by negative 2, and x is going to equal 0.6011. All right, so that's representing x, which you put with the 69. So that's going to be the decimal form of the percent. So that's not the percent. If you want to get it into percent form, just multiply it by 100. So you have 60.11%, and that number goes with the gallium-69. Okay, so you do have to label these here because you're going to get two answers. That percent goes with the gallium-69. The reason why I know that goes with the gallium-69 is because I solved for x and I put x with the 69 isotope. All right, so then how do you figure out the percent of the other isotope? Well, think about it. Both of these percents should add up to 100. So if you take 100 minus the 60.11, you would get the other percent. So it should come out to be about 39.89%. All right, that's how we got that one. And this one's going to be the gallium-71. Okay, so those are your two answers here. Notice they would add up to about 100%. And that's how you would do one of these problems. People always say, well, what if I put X with the other isotope and 1 minus X with the 69? Your work would still come out to be the exact same answers as long as you paid attention to which one you put with X. All right? So you're still doing a decimal times mass problem. The key is you don't know the decimal. So you have to do an x and a 1 minus x. As soon as you look at one of these problems and you know that you don't have the percents and they gave you the average, in your head you got to say, okay, it's going to be an x and a 1 minus x problem. Not an x minus 1. It's a 1 minus x. All right, so it's just a different form. Typically, you just do decimal times mass for every isotope and add them up. But when they don't give you the percent, in your head, you immediately say, okay, this is going to be an x and a 1 minus x version. All right, so make sure you can do both variations of an average atomic mass problem.